Hello. Oops, just dropped my pencil. We are going to discuss bond energy today and enthalpy. If you get your purple packets out and open to page 16, halfway down the list there, we're going to define the term enthalpy. So far we've talked about heat, and we've talked about heat transferring from one object to another, and that's what we use Q equals MCAT for. Now we're going to talk about heat that comes from within a chemical reaction. If you stop and think about a chemical reaction, you have atoms and molecules that rearrange. Those atoms that are bonded to each other, therefore, their bonds have to break, and then the bonds have to reform. That energy is called enthalpy. All right? Enthalpy is the internal energy of the system. Okay? We can't measure enthalpy directly, but what we can measure is the change in enthalpy. For instance, if we're talking about a chemical reaction and we know the energy the reactants have and we know the energy the products have, the difference between those is the change in energy, and we can calculate that. There's several ways to do that. The first way we're going to learn is by breaking and reforming bonds. All right, I want you to add this in to your information though. I want you to add in, we cannot measure enthalpy directly, only the change. Enthalpy, we use the letter H, the Greek letter H, eta, for enthalpy. And for our purposes in here, enthalpy and heat are going to be synonymous. All right? When you stop and think, all right, H stands for heat, it almost makes sense, but really it stands for enthalpy. All right? So we're going to use enthalpy, enthalpy or heat of reaction. Sometimes you can, instead of saying the enthalpy of the reaction, you can also say the heat of the reaction, meaning the heat evolved in the reaction or used up. All right, so we're going to look at bond energies, okay? When we have a chemical reaction, those bonds in the reactants break, and then they reform in the products. If we know the energy that those bonds have, we can calculate how much energy or how much enthalpy the reaction is going to have. All right? So bond energy or bond enthalpy is the amount of energy it takes to break 1 mole of a bond in the gas phase. Bond energies are always positive. Chemical reactions involving breaking bonds in reactant molecules and making bonds to create the products. The overall enthalpy for a reaction, and this is enthalpy of the reaction, can be calculated as the sum of the enthalpy changes associated with breaking the bonds and forming the bonds. Okay? And here you can see a list of bond energies. Notice they are all positive. It takes energy to break a bond. We talked a little bit about endo and exothermic. Endothermic energy is going in, so energy is positive. The bond energy, if you're breaking the bonds, that's positive. When the bonds reform, that's negative energy. That is energy that's being released. The bonds are more stable. After 2 atoms become a molecule, they're more stable, and they release some of that energy that they had before when you broke the bonds. It's kind of like, think about Legos. It takes a lot of energy to break the Legos apart. Okay, and then you have to put them back together in a new format. That putting them back together is the bond energy being released. All right, when we use bond energies to estimate, and that's important, that's another important word here, estimate. Bond energies can be different depending on the other bonds in a chemical. So we're only talking about estimations here. We only can get estimated enthalpy changes from bond energies. The bond energy depends on the surrounding atoms. We use averages. If we are breaking a bond, it's endothermic. And it'll be positive. If we are making a bond or forming a bond, it's exothermic. And it will be negative. Okay? And we might as well fill this in real fast since we're here. A delta H, remember that's enthalpy, is if it's positive, I'm just restating what we just did. It's an endothermic reaction. That means it'll feel cold to the touch. Okay? Energy's going in. The ice cream freezing was not endothermic. We were removing energy from the ice cream. The energy was going into the ice to melt the ice, and it was able to melt the ice because of the salt. So the ice cream was exothermic. I use RXN stands for reaction. Okay? Endothermics are going to have a positive delta H's. Exothermic is going to be a negative delta H. A breaking bond is endothermic because bond breaking energies are always positive. Bond forming is negative. All right. Let us get down to the meat of the situation. Take a look at the handout for today, Calculating Enthalpy Change Using Bond Energies 2. Okay? What we're going to do is we're going to practice drawing some chemical formulas and calculating those bond energies. The first thing we need to do is write the balanced equation for the combustion of propane. Propane is C3H8. Combustion means it's burning with oxygen. When it burns, it forms carbon dioxide. This is something we learned in December. And water, maybe November, I'm not sure. Water. Okay? Next thing to do is balance it. We have 3 carbons, so we're going to need 3 carbon dioxides. We have 8 hydrogens from the propane, so we'll need 4 waters. 4 times 2 is 8 hydrogens. We have 3 times 2 is 6 oxygens from the carbon dioxide, 4 more from the water, so that's 10, which means we would have 5 pairs of oxygen. Now the next thing is a little difficult because we haven't learned molecules yet. This book, actually bond energy comes while you're learning molecules in the book, but I like to teach it with energy, so I moved it. Okay? So we don't know how to do Lewis structures yet. If you did honors chemistry, you probably did some Lewis structures. We're going to draw propane. Propane is 3 carbons for the backbone, and then each carbon is attached. Hang on, I'm going to erase that so it doesn't get confusing. To hydrogens. The end carbons are attached to 3 hydrogens, and the middle carbon is attached to 2 hydrogens. How do I know this? I took organic chemistry. You would probably be given, you wouldn't be expected to draw that. Oxygen is actually double bonded. There's 2 oxygens and they form a double bond because oxygen has 6 electrons and he needs 2 more to be happy. So each oxygen shares 2 electrons with its partner. We have 5 double bonded oxygens. Carbon dioxide, carbon is double bonded to 2 oxygens in each case. Hello again. I got distracted by a phone call. Okay, so we had been talking about bond breaking, and I had just drawn the 3 carbon dioxide molecules with their double bonds between the carbon and the oxygen. Finally, we have to do hydrogen and oxygen. Hydrogen bonds to oxygen with a single bond. So we're going to draw 4 of these. Now, we're going to use this table and calculate the enthalpy change from bonds breaking and reforming. If we look down here to step 4, it says calculate bond energies. First, we need to count how many carbon-hydrogen bonds we have. I almost said calcium. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 carbon-hydrogen bonds. Each carbon-hydrogen bond, here's carbon and here's hydrogen, requires 413 kilojoules. Remember, that's an average. 413 kilojoules of energy per 1 mole to break. All right. Carbon-carbon. Change colors here. We have 1, 2 carbon-carbon bonds. Each carbon-carbon, here's carbon-carbon, is 346 kilojoules in a mole. Third, we have oxygen, and there are 5 double-bonded oxygens. Double-bonded oxygen is 498. So we do the math. 413 times 8 is 3304. You all should be calculating along with me. 2 times 346 is 692. And 498 times 5 is 2490. We add all those up and we come up with 6,486 kilojoules of energy per mole that went into that reaction to break all of those molecules apart into atoms. Now we're going to reform. Go to a different color. We're going to do carbon to oxygen. 1, 2, 3, 4, 5, 6. And carbon to oxygen. Here's carbon to oxygen, 358. Except for they're double bonds. That wouldn't work. Erase that and go back. Carbon to oxygen in a double bond is 799 kilojoules. Last but not least, we're going to do our hydrogen oxygens. There's 1, 2, 3, 4, 5, 6, 7, 8. The hydrogen oxygens are right here, 463. So 799 times 6 is 4,794. 463 times 8 is 3,704. That adds up to a total of 8,498 kilojoules per mole formed. Remember, forming means they're more stable. They're going to release their energy. Because they formed, that's exothermic. They're releasing their energy. So we're going to combine the two. We're going to take our bonds that broke, 6486. They're endothermic, they're positive, and we're going to add that to these bonds that formed, which is 8498. But we're not adding it, we're subtracting it because they're exothermic, they're giving off energy. When we take 6486 minus 8498, we get negative 2012 kilojoules per mole for that reaction. Okay? The next page, we're not going to do the bottom part, because again, you don't know how to do Lewis structures, but we have Lewis structures drawn for you. You're going to complete these 5 equations. Your bond energies are up in that little box. So remember, it's going to be the bonds breaking minus the bonds forming. So your hydrogen bonded to a hydrogen is going to be 436 kilojoules. Chlorine bonded to chlorine, 242. You can add those together. Then you'll do hydrogen to chlorine, and there's 2 of those guys. So you'll do 2 times 431, and then subtract that from the sum of the hydrogen and chlorine bonds. Okay? Might want to do this on a separate sheet of paper so you have more space, but if you want to cram it in there in the little boxes, you're sure welcome to. I did mine on a separate piece of paper. That is your homework for tonight. Tomorrow we will continue this conversation and we'll start talking about the enthalpy of reactions that we can find in different ways. All right. Thank you very much.